In assignment 220, let's try to extend our familiarity and connect some ideas about derivatives. So in question 2, we're asked to think about the graph of x cubed, and it's a typical function that we look at in calculus because it has that saddle point where the tangent temporarily has a slope of 0. Everywhere else on the graph, our tangents show that we have a positive slope. So we could say that the function is increasing everywhere. So each point, remember our definition for increasing is as x moves to the right, do our y coordinates move up. And in fact, that does happen here over the entire domain. So our power rule for f prime of x would be 3x squared. So where is f prime of x greater than 0? Well, notice 3x squared is always greater than 0 everywhere except when x is equal to 0 itself. So from negative infinity to 0, union 0 to infinity. Another way you could say that with your algebraic notation is it's greater than 0 for all x where x is not equal to 0. So that would have been an alternate form, but much more common now that we would use our interval notation. So 3x squared is in fact positive. That's the slope of every tangent line, except when x is 0, then our derivative will be 0. Of course, that means that the tangent line is horizontal. Okay, so let's put this together. If a function is increasing over an interval, does that mean that its derivative is always greater than 0 over that open interval? And that would be false because it could have a slope of 0. And there's actually another case we're going to see later where the slope could also be undefined. So we could have a horizontal tangent or a vertical tangent, and our function could still be considered increasing. So there's always the exceptional cases that you have to think about. In our next question, we're interested in the cube root function. So the cube root function, now you can see that instead of having that saddle point where we have a horizontal tangent, now we actually have a vertical tangent in the middle of the graph. But look at every other tangent on the cube root function. Every other tangent, this is our f of x equals cube root of x function. So every other tangent seems to have a positive slope, but here we have a vertical tangent. So when we have a vertical tangent, we would say that f prime will be undefined. So f prime at 0 is undefined. Okay, so our questions are, where is f of x increasing? Well, as we move from left to right, our y coordinates are always getting larger. So the function is increasing over negative infinity to infinity. Where is f prime going to be greater than 0? F prime is the slope of the tangents, and it will be greater than 0 everywhere except at 0. So from negative infinity to 0, union 0 to infinity. So the open endpoints here are what's excluding the 0. All right, so let's check that out and see why it works algebraically. Our power rule says bring down, this is x to the 1/3. I should write that as an exponential function. So we bring down the exponent 1/3 and we subtract 1 from the exponent, so we would have negative 2/3. And another way that you might prefer writing that as a fraction is now we would have the cube root of x squared in our denominator. So, of course, because our variable is in the denominator, you can see that f prime is not defined at 0 because we would have division by 0. And what does that mean? It means that as we get closer and closer to 0, the limit of this fraction is going to go to positive infinity. So you can see the tie-in from our derivative unit back to our limit unit. So as x approaches 0 from the negative side, think what happens if you put in a very small number in the denominator, like 1 over 1,000th or a billionth or a trillionth. So we can see what's going to happen here is that as we get closer and closer to 0, our denominator gets small. We multiply by the reciprocal. That means that the fraction is going to go to infinity. And why does it go to positive infinity? Because we're squaring the x first. So even though x is negative, we're squaring it to make it positive. So we know that the same thing is going to happen on both right and left ends of the graph. We're going to, or I'm sorry, on both the left and the right sides of 0, our derivative is going to go to infinity. Okay, so let's check out the true-false question. If a function is continuous and increasing, then its derivative is greater than 0. This should say or. Its derivative is 0, or its derivative is undefined. So those are our 3 cases. So I think we want to say that this will be true. Those are the 3 possibilities if a function is continuous and increasing. All right, let's go to our next common function, the square root of x. So here's our square root of x graph. And I hope immediately now you're starting to think in terms of these tangent lines. And it looks like the tangents are always going to have positive slopes everywhere except here at 0, we have a vertical tangent. Now, you might not be positive of that yet. If it is a vertical tangent, we'll be able to tell that by looking at our equation for the derivative. So let's come back to that here in a second. So our question over what interval is f of x increasing. As x, if we choose an x greater than the previous one as we move to the left, are our y coordinates always getting larger? And they are. So this graph would be increasing from, and we can actually include the closed endpoint or not. That's not going to be a big deal here, but our endpoint is actually closed here. And let's take a look at f prime of x. So let's actually do our power rule down here first maybe. So our f of x, the square root function, is x to the 1/2. So our power rule tells us that its derivative, we bring down the exponent, we subtract 1. So another way of writing this is 1 over 2 square root of x. And this I would now like you to be so familiar with because we often do the derivative of the square root of x. And as soon as you see this square root of x in the denominator, notice the domain of f of x. The domain, I'm sorry, of f prime of x. The domain, we can't put a negative under the square root sign, and we can't put 0 because it's in the denominator. So the domain of f prime is an open endpoint. So notice the domain of our original function had a closed endpoint at 0, but our derivative function is only going to be defined greater than 0 because the derivative would give us division by 0. Okay, now let's think about this. Let's think about what happens if we choose a number. If we choose a number for x that is just slightly larger. If we do the number that is almost at 0, but from the small side, I'm sorry, from the large side. So if we put in a number like 1 billionth or 1 trillionth, notice that the denominator is very, very small. So when the denominator is small and we multiply by the reciprocal to move it to the numerator, so dividing by a small number gives us a huge number. So we could say as x approaches 0 from the right side, f prime of x is going to get huge. It's going to go to infinity. So where is f prime greater than 0? The graph of the derivative is actually going to look like this curve, and f prime is going to be greater than 0 everywhere from 0 to infinity. So it'll take some time, but we'll get used to these. Okay, so let's try to use this, and let's use the definition of derivative. So we're starting with f of x is the square root of x, and I'm going to prefer, you may or may not prefer using the rational exponent or the radical. I'm going to prefer the radical, but either way should work. So you only have to pick one of your two definitions. So let's say f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x. You can substitute right away here. You don't have to write these definitions. So in this case, I'm going to use the square root of x as my value. So I'm going to have f of x plus h. I'm going to have to put that binomial into our square root function. And f of x, of course, is just the square root of x. And if I did direct substitution, if I let h go to 0 right now, we would have 0 over 0. So our trick when we did our limit unit, if we have the difference of square roots, I hope you would remember the trick of multiplying by the conjugate. So let's rationalize the numerator. And the reason we're going to do this is so that we can cancel. So notice what happens now in the numerator. We get an x plus h from the first terms, and we get a minus x from the last terms. The outside-inside terms, when we FOIL, of course, would be canceling out. And our denominator, I'm not going to distribute because I think something is going to cancel here. So, of course, what we're expecting, this positive x, negative x are gone. And now notice what we have here. We have an h over h, so we could leave a 1 when we cancel those. So now we've solved our 0 over 0 problem. You need not write this again, but I want to make sure everyone is with me. So I'll show you that this is what we have left at this point. So now by direct substitution, we are ready to do the limit, and h is going to go to 0. So look at what we would have. We would have 1 over the square root of x plus the square root of x. No more limit. I just did the limit. Let's erase that symbol. So we could rewrite this then as 1 over 2 square root of x, which is what we got when we did the power rule. So we were expecting that answer. Okay, you only needed to do one form or the other, but let me scroll and repeat the process for those of you who did the alternate version. So if we limit x going to a of the difference of our y coordinates over the difference of our x coordinates, in this case, it would look like the square root of x minus the square root of a. And here, for the first time, the two methods are almost the same. We're going to multiply by the conjugate to rationalize, and that's going to remove our 0 over 0 problem. So not too much difference here. Here we'll have an x minus a in the numerator. So those will cancel to leave a 1 in the numerator, and then we can do our substitution. X is going to become an a. So here we are already at our answer, 1 over 2 square root of a. All right, let's see what we want to do here. So now we're just taking a look at some values here. So we're still working on our same function. When f of x is the square root function, we found out that f prime of x is 1 over 2 square root of x. So we're just practicing here, and this is a perfect square. If I can count the zeros here, it looks like we've got 6 zeros. so that this is a perfect square. So f prime of 1 over this value would be 1 over 2, and the square root of that value would have 3 zeros. So we would get 1 over, oh, I'm sorry. Let me change my mind about that. I better take some more space here. F prime of, I'm doing the denominator here. Watch what I did wrong here, guys. I wanted to put this. There's a complex fraction here is what I was doing wrong. So a fraction inside of a fraction. So this is going to be 1 over, and then we'll have 2 over 1,000. In other words, this is 1 over 500. So when we multiply by the reciprocal, this is going to go to 500. So be careful about complex fractions. Our second case is the one that I was actually doing first. So this would give us the square root of this value, and I guess you guys know the square root of that value is going to be 1,000. So here we're going to get the small fraction. So the point is that with reciprocals, they're actually going in the inverse direction. So when we put in a small fraction, our derivative gets huge. When we put in a large number, our derivative is going to go to 0. So now we can sketch a graph of f prime of x. So the reason for question F was just to make you think about what's going to happen when you graph this. So as we get close to 0, it is going to rise to infinity. And as we go towards infinity, it's going to get closer and closer to 0. So this is our graph of f prime of x. Now, you aren't asked to graph them on the same function, but let's look at where f of x started. So let's see if this looks like the slope of tangents. Here, our tangent line has a huge slope because it is vertical. Over here, our tangent lines are almost horizontal, so they're going to go to 0. And here, our tangent lines are in this middle range of positive values. So notice our derivatives are all above the x-axis. F prime is always positive because our square root graph is always rising. The only place we have a defined value on f of x, but it is undefined because of the vertical slope of the tangent. All right. Hopefully that wasn't taking too much time here. All right, what if we want to do our power rule, but we have a polynomial divided by a monomial? When the denominator is a monomial, we know we can divide it into each term of the numerator. So your first step is to just divide each term of the numerator by x to the third. When we're dividing, we'll subtract exponents. So of course this problem, once we rewrite it, now we can find f prime of x by using the power rule very simply. And the derivative of a constant, remember, is just 0, so we're not going to write that. Okay, our question 6, this is our Leibniz notation for a derivative. So find dy dx. dy dx is the answer that you get when you do a d dx operator on each side. The d dx is the operator, and the result that we come up with on the right-hand side is dy over dx. And on the right-hand side, the slope of this term is, of course, just 3.2. So dy dx is similar to just saying, please find f prime when it's given in function notation. Find dy dx, so this is another term for slope. It should remind you, by the way, of delta y over delta x. That's why Leibniz chose this notation, because for slopes we did delta y and delta x. So now we're doing dy dx. So the d for derivative and for delta. All right, so if we start with y equals a constant and we put this d dx operator on both sides, the derivative with respect to x gives us dy dx, and the derivative of a constant gives us 0. We know that the slope y equals c, we know that it is a horizontal line, and we know that the slope of the tangent lines will all be 0. So the derivative of any constant will be 0. All right, let's see. F of x. Here's our parabola function. F prime of x, we know by our power rule that f prime of x is 2x. So our derivative of this parabola is this straight line with a slope of 2. And let's think about that. On this side of the graph, doesn't the parabola have all negative slopes? So the derivative is below the axis. And on this side of the parabola, doesn't the parabola always have a positive slope? So our derivative is above the x-axis. So f prime of x is that linear function. All right, in 8b, we have the square root function as our original graph. Let's take a look at it. And this is one that you're not going to do with a formula. You already know the slope on this side is positive 1, and you know the slope on this side is negative 1. What happens here at the corner? Because the left and the right derivatives do not agree, we have to leave an open circle. So from this point to the right, our slopes are always positive 1. From this point to the left, our slopes are always negative 1. At the corner, we have one tangent going in the slope of positive 1 and the other tangent going with a slope of negative 1. How could we choose a derivative? We can't choose the slope. So there is no derivative. There is no derivative at a corner because the tangent from the left side and the right sides do not agree. So the left derivative is not equal to the right derivative. So we can't choose at a corner, so there is no derivative. All right. We can quickly find f prime of x here using our power rule. So we can find the slope of our tangent line by substituting. So our slope of our tangent will be 12, and we need a y-coordinate on f. So we'll have 7 minus 2 or 5. So our point of tangency and our slope. So our tangent line, I am hoping that you're able to do these quite quickly now. They're very important. That's why we keep practicing equations of tangents. And the same problem with the equation of the normal. I always read carefully, but it's the same point of tangency here. Let me make that a little more clear. Negative 1/12. All right, let's see if we can, we're taking a long time here, but I think we're almost done. So here we think of f of x as x to the 1/3. So our power rule tells us 1/3 x to the negative 2/3. Did we do this problem a minute ago, or is it one that was similar to it? So we want the cube root of x squared. These would be equivalents. You can do one or the other. You don't have to write both. Okay, so now let's use this. F of negative 8 would be the cube root of negative 8. So our point of tangency would be negative 8, negative 2. F prime of negative 8 would look like the cube root of 64. The cube root of 64 is 4. So we would come up with 1/12. So I didn't leave much space here. Let me scroll over a bit. So our tangent line y plus 2 equals 1/12 x plus 8. And then our normal line for the same problem. Let's just use -12 as our slope. I'm going kind of quickly here. I hope my arithmetic doesn't fail. But our video is getting pretty long. All right, and one more. Let's find the equation of the tangent. So we could find f of 2 first. 3/2 2 to the -4th. So 3/2 times 1/16, 3/32 for our point of tangency. And f prime, we have to do our power rule, so we bring the -4 and multiply, so we'll have a -6 x to the -5th. So again, you can move these to the denominator if you wish. So f prime at 2 would be -6/32. Let's make that a -3/16 as our slope. So our tangent, y minus our y coordinate, our slope, x minus our x coordinate. I think that should be right. And finally, our normal. All right, so that was a lot of talking. Positive slope, sorry, perpendicular lines, change the sign. And that should do it.